What the sentence means: document databases reverted back to the hierarchical model in one aspect, storing nested records, one-to-many relationships within their parent record rather than in a separate table. This means, first, relational databases separated related data into different tables. In the screenshot, a LinkedIn profile is represented using many tables: users, positions, education, regions, industries, contact info. Each small piece of data lives in its own table, usually connected through IDs, foreign keys. This is exactly what we talked about earlier. Meaningful human data like philanthropy is stored once in a lookup table. Other tables store only IDs, not duplicated text. This avoids duplication and makes updates easier. This is the relational model. Second, document databases don't split this out into tables. Document databases, MongoDB, Firebase, CouchDB, etc., store related data inside the parent record, like this. This is hierarchical tree, just like the old mainframe databases, which is like kind of like the network model. So a document, it's just reiterating that document database kind of repeat or just copy the previous version of hierarchical model, especially in storing nested records, one-to-many relationships, because hierarchical is also storing one-to-many. So each small piece of data leaves its own table now in the relational database, usually connected through IDs. So meaningful human data like philanthropy is stored once in a lookup table. Other tables store only IDs, not duplicated text. This avoids duplication and makes updates easier. This is the relational model. How it connects to our earlier conversation. Earlier, you asked about IDs versus storing human readable text directly. Relational DB, store IDs, no duplication. Document DB often stores the full text in every document. Duplication happens. So a document DB actually stores the full text instead of ID. So there's more duplication, but it's less complexity when it comes to application code. So the sentence in our screenshot is pointing in this exact difference, because you're better normalize your data in relational database, and you less normalize it in document database. But document database is easier because it's closer to application code. So it's really up to your goals. How it connects to the screenshot. Relational version, many small tables linked by IDs. Everything is normalized. Philanthropy appears in industry's table, industry underscore name. The user's job links to industry using industry underscore ID. Grids shuttle area appear once in regions table. The screenshot is showing how complicated relational schemas become, because every nested concept becomes its own table. So we saw also how a relational database, because of a lot of table, become complicated, because every nested concept becomes its own table, even if it doesn't have to do with its relationship. So in document.datamiddle, we just leave it as is, and all of the document related information are in one document. Document version, one big nested record. The book says document DBs reverted to hierarchical because of position, education, and contact info would all be stored into the user record directly, not in their own table, just like our relational databases, which is the opposite of relational database. In one simple sentence, the sentence means that document databases store child objects like positions, education, contact info inside the parent document instead of splitting them into separate tables connected by IDs the way relational databases do. This ties directly to our earlier discussion about avoiding duplication, which is done by relational databases, uses IDs, hierarchical versus flat structures, how relational DBs break everything into tables, why document DBs feel more natural but duplicate more data. Better performance due to locality. What it means? Locality equal data is stored together. So a document database actually have better locality. Remember the locality, the spatial and temporal locality we discussed in OS. In document databases, MongoDB, etc., a user record contains positions, education, emails, contact info inside the same big JSON document. When the application fetches the user, it it loads all of that at once because it's stored contiguously. This is faster because it results in fewer disk reads. It matches how CPU and operating system cache data. So because you need to load all the document instead of loading multiple tables that could be in another disk, you just load it once, so you reduce the IO in document database. It also matches how CPUs and operating system cache data, which is spatial locality. So remember, a database has an OS, so it needs to deal with the OS because it's a user program. So whenever the OS will deal with caching its data, whenever the database requests that same document again, it doesn't have to. So since it follows that, it also applies those same caching, which leads to faster read or write. So is this related to LRU or MRU caching? Yes, but indirectly. Locality helps because OS loads data in pages, CPU loads data in cache lines. So remember the cache lines, the shorter or the nearer you are in CPU, the faster you are. That's why the GPU is nearer. And also the page concept of OS, how it actually stores memory, and how virtualization of these pages actually help indirectly with security because the user space code or program doesn't know the exact physical location. Caches a fixed item using LRU or MRU policies. When data is physically near each other, it fits into the same pages or cache lines. Fewer misses. So because the document database are near each other, so they also fit with the OS cache or the cache lines, which meant you have fewer misses on your database. So that's the advantage of document database over relational database when it comes to caching. It has an advantage of spatial and temporal locality already produced by OS. But the book isn't specifically talking about OS caching algorithms. It's talking about just the database user space code. It's talking about the general idea that loading adjacent data is faster. Closer to the data structure used by the application, applications often use objects or classes like class, user, inside this is name, position equal empty array, education equal empty array, contact info, and the close semi-curly bracket. The tree-like structure maps naturally to a document database. So this class, when you create a class in object-oriented programming, it is more like a document database than a relational database. And as you can see, you follow the same kind of like an object-related pattern in document database. In a relational database, this is split into 6+ tables with foreign keys. So instead of just one document, you will split this in 6 tables with foreign keys to reference those related record. So it has an index. In the future video, we will discuss how storage engine provide index in each table to be able to help them reference each record using foreign ID. So that's what we do with relational database. For document database, you use document reference, but it's the same. It's almost the same. You use to reference records. So in relational database, you actually need to index that. So let's say you want to query it differently, you would need to create another index or to index that to be able to implement that query. While in document database, you don't need to create these 6 tables. So this sentence means document DB equal matches how programmers thinks. Relational DB equal matches how mathematician thinks. This is directly connected to our screenshot. Is this related to data structures and algorithms? Yes, strongly. Jiwen Grow explained continuous, or our previous video explained contiguous data structure. Arrays, fast because of locality. Non-contiguous structure like linked list or node, slower due to poor locality because they could be spread along the memory. Document data records often behave like arrays of nested objects, which have better locality compared to relational DB joins, which behave like pointer chasing like linked list. So relational DB behave like a node data structure or linked list. That is why the table is not actually a table. It's actually a linked list, kind of like a linked list under the hood. We will get more clarity in this as we progress. In the book, Wengrow gives example, or in our previous video, we give example such as arrays being faster because they sit next to each other in memory, linked list being slower because data is scattered. This is exactly the same principle. So yes, the explanation helps you understand locality concept. Schema flexibility, what it means. Relational DB, you must declare a fixed schema. Every row follows the same structure. So in the relational DB, you set a schema first, and each row on that table must follow the same structure. Adding a field requires alter table, risk. So you have a risk in that in migration. In document DB, each document can have different field. No rigid structure. You can add fields gradually, mix types, etc. So a document's kind of like row in a relational database. It doesn't have that rigid schema. So you don't risk having a problem with migration. So you can add fields. So in relational DB, you can't just add field and you use alter table to add field because they're kind of like altering the entire table structure because the schema is inflexible unlike the document database. So you can add fields gradually, mix types, etc. Example, document 1, name, colon Alice, comma, age, colon 21. Document 2, name, comma, Bob, comma, hobbies, colon, golf. Now, no problem. This is what the book called. So that's what we talk About schema flexibility, what does the whole sentence mean as a whole? Here's the full sentence. The main arguments in favor of the document's data model are schema flexibility, better performance due to locality, and that for some application, it is closer to the data structure used by the application. The relational model counters by providing better support for joins and many-to-one and many-to-many relationships. The entire meaning summarized: document databases don't force a strict schema, flexible, store related data together faster, locally, map naturally to code, nested JSON-like objects. Relational databases are more rigid but better for relationships, joins many-to-many, avoid duplication via IDs since you are normalizing it. Keep data consistent and normalize. This ties directly to all our previous messages about IDs versus text duplication, relational versus hierarchical models, the many tables in your screenshot, why document DBs embed nested records, why relational DBs split everything. Does Query Optimizer relate to TCP or IP? No, they are completely different domains. Query Optimizer decides how to run SQL queries efficiently. Choose indexes, join order, execution plan. Related to database internals. TCP or IP, networking protocols, routing, packets, congestion, control sockets. Does underlying TCP or IP illustrated help you understand DB Optimizer? No, it does not help at all. They solve different problems, use different theories, and operate at different layers. Our previous messages about networking do not help in understanding SQL optimizers. How does this look in real code? Document DB example in MongoDB. db.users.insert1, opening parenthesis, opening semicolon. Next line, name, colon, quote, Bill Gates, comma, next line, positions, colon, opening square bracket, next line, opening semicolon bracket, company, colon, quote, Microsoft, comma, title, colon, quote, CEO, closing semicolon bracket, next line, closing semicolon bracket, comma, next line, education, colon, opening semicolon, next line, opening semicolon, school, colon, quote, Harvard, comma, start, colon, 1973, and then all the closing remarks. So this just copy or just represent the previous table in document database model. Now one read, you get everything. In relational DB example, you have users table, positions table, education table. Now for querying it, here's the code. Select asterisk, next line, from users u, next line, left, join positions p on p.user underscore id equal u.id, next line, left, join education e on e.user underscore id equal u.id, next line, where u.id equal 251 semicolon. The query optimizers examines indexes, join order, cost estimates, available statistics, and chooses the fastest path. So when you do this, you're just declaring what you want to do, and the query optimizer indexes it. So we will discuss that in storage engine, how log structure index the data, and how B-tree is the most common use storage engine for this transaction database. A join order, so it actually does the join order. It does that through merging and compacting, compressing and decompressing in its user database code or storage engine code, and chooses the fastest plan. It also keep a record of those indexes to track all of those retrievals, to check the available statistics, etc. Final summary, all connected to our previous conversation. Document DBs embed nested data, fewer tables, more duplication, better locality. Locality equals faster because data is stored together, fewer disk and cache misses. This does relate to CS concepts like arrays versus linked list, exactly like the previous video we discussed. Schema flexibility, no fixed schema. Relational DBs are better for joins and relationships. Query optimizers have nothing to do with TCP or IP. Real code looks like MongoDB JSON versus SQL join queries. Fewer disk reads, does it mean never talk to this again? No, it means fewer, not zero. When you load a document, i.e. Big Firestore document or MongoDB doc, one disk read pulls in a whole block or page in the OS or in the SSD. That block contains most of all fields because they're stored together. So it's not zero. It's one, at least, at the minimum. After that, the OS caches this in RAM, page cache. The CPU caches part of it in L1, L2, or L3. As long as your data fits in those caches, no more disk reads. So these RAM and OS caches are discussed in the previous video. But if you query different users, your app restarts, your cache evicts old pages, then the DB must talk to this again. Since you restart your PC and you query different user, that DB must talk to this. Therefore, there's an I/O. So the sentence better performance due to locality means because the data is stored contiguously, one read brings in everything you need, and the OS or CPU caches keep it around longer. Locality is not equal zero disk access. Locality equal fewer disk pages plus better caching equals faster. How locality connect to OS 3 easy pieces? OSTEP teaches paging. RAM is divided into pages. This is also read in pages. Locality principle, temporal plus spatial. Temporal locality, recently used, use again soon. Spatial locality, nearby items accessed together. Document DBs exploit spatial locality because nested data sits together. So in the principle we discussed in OS 3 easy pieces, the one that is being taken advantage by document database model is the spatial locality. OSTEP helps you understand why reading one page is faster than reading 20 pages, why scattered relational joins cause more disk 6. So that's your relational database. Why document DB embedding reduces random I/O. So there's a pros and cons. You get more duplicate in document database, but you get less I/O because you get this advantage of spatial locality. So OSTEP helps you understand locality but not query planning. So how the previous DSA we discussed connects. It's very connected because arrays equals contiguous memory, good locality, fast. Linked list, that's why the read is O1 in array. Linked list equals scattered memory, bad locality, slow. This is exactly the same principle as document DBs equal arrays of nested objects, contiguous. So in document DBs is actually an array. The data structure of that document DB is an array because it's contiguous. Relational DB, a bunch of foreign key joins like chasing pointers. That's why we compare that, or we analogous that to a node data structure. So the previous chapter or the previous data structure and algorithm we discussed gives us the mental model we need why document DB reads are fast, why relational joins require many pointers, more disk or page loads. So it's a simplified version of locality argument. How Ackerman's full stack and mastering Node.js relate to this? So in different layer, this helps the previous videos we discussed help us understand JSON handling, REST APIs, node buffers, express request parsing, middleware, how web apps move data around, how to structure front end or back end, but they do not help us understand SQL Query Optimizer. We will actually discuss that in the future video, how the internals of this storage engine works. Execution plans, index selection, join strategies, database internals. They help you understand how apps use database, not how DB optimize queries. Because remember, database are actually an abstraction. So is JSON array really under the hood? Important, JSON is not a low-level structure. It's a serialized format. Under the hood, in memory, when your node or browser parses JSON like this, code user colon array of 1, 2, 3, it becomes JavaScript objects plus arrays in memory. So like this in JS, open curly bracket, next line users colon an array 1, 2, 3, and then it will be converted to assembly or a binary. So the array is a real array, but JSON just text. On disk, MongoDB, Firestore, CouchDB, they do not store JSON text. They store binary encoded representation, BSON, Firestore binary format, etc. JSON is only used for API communication, for coding, for dev tools, for representing structured data to humans. Do I need NPM to get JSON? No. JSON support is built into browsers, Node.js, Python, Java, Go, C, almost every language. Example, JSON.parse, JSON.stringify. So that's what language do to parse it. But in browser, it's actually fully supported in the Node.js application. This comes built in. You do not install anything. NPM libraries may help with schema validation like Zod or JOI, but not JSON itself. Why does VS Code support JSON? VS Code supports JSON because it uses the Monaco editor. The browser engine inside VS Code parses JSON. Language servers provide autocomplete plus validation. This is not OS level, it's editor level or user space level. How all of this connect to your LiveKit plus Firebase full stack app? Look at your app architecture. app/function/live/public. You use Firestore, a document database, Firebase functions, serverless, Next.js, React, JSON for all API inputs or output. Every Firestore document you write, like await set doc, argument docrep, or parameter docrep, open curly bracket, next line, patient name colon, code John, next line, consultation history, colon, and then, an array, next line, contact info, colon, and then an array, then closing remarks. It's stored as a single document. Read back with one disk or page load. It benefits from locality. Compared to SQL, you would need 6 tables plus join. Your Live Firestore app is a perfect example of document DB advantages, schema flexibility, one document equal everything need for a page, locality makes reads fast, especially on mobile, no joins needed, natural mapping to React components or JSON structures, relational DB disadvantage for your use case, you need joins for consultation history, more tables to more disk grids, harder scaling, more rigid schema. That's why it's hard to integrate all of the schema on your Firebase app or Firestore app. It's because it's hard to scale this document data model. But have you used a relational database? It would be faster. The book's explanation maps directly to your architecture. Now, Query Optimizer versus everything else. Query Optimizer is its own world. Cost-based selection, index planning, predicate pushdown, join ordering, execution plans. What helps you learn it? Book TCP/IP Illustrated helps with Query Optimizer? No. Why? Networking, not database. OSTEP, indirectly, helps you understand paging and caching. Data structure and algorithm? Yes. Locality, arrays, pointer chasing. Full Stack Web by Philip Ackerman? No. Application level. Mastering Node.js? No. It's runtime level, not DB theory. So the best books for query optimizers are Database Internals by Alex Petrov, Designing Data Intensive by Martin Kleppmann. Final summary, Document DBs like faster, fast because one retrieves a well-nested object, better locality, fewer page loads, fewer disk calls, maps naturally to React or Node JSON structures, flexible schema, matches rapid product development, perfect for your teleconsultation app. Relational DBs, better for joins and complex relationships. IDs avoid duplication but require more I/O. Query optimizer needed because data is scattered. Books relationship, data structure and algorithm helps understand locality plus pointer chasing. OSTEP helps understand paging or caching behind DB locality. Ackerman helps understand full stack usage of JSON. TCP or IP illustrated not relevant. Query optimizers best learned from DB focused books. Oh my, so big. This is a lot. So let's start here. Let's continue. JSON becomes JavaScript objects plus arrays, but JSON is a text. JSON equals a text format. So like this example, JSON name colon kpol age colon 22. This is literally just characters like NAME, so like string like this. This next has no type information, no pointers, no byte level structure. When you call JSON.parse, the text is converted into real data structure. Example in the JavaScript, const obj equal JSON.parse, and then open parenthesis, code, open semicolon, code A colon 1, comma, code B colon, array inside it is argument 2 comma 3 closing. Now obj is not text, it becomes a real JavaScript object containing real JavaScript arrays containing real JavaScript numbers. These live in RAM with native memory layout. So JSON in text, human readable, JavaScript objects in RAM, machine data structures. JSON in text characters, JavaScript objects in RAM, pointers, arrays, numbers. JSON in text slow to process, JavaScript objects in RAM very fast. It's exactly like a recipe written on paper becomes actual ingredients when you cook it. JSON is the recipe, JavaScript objects are the food. How can JSON be text and objects? Because only the file or transmission format is text. When LAN or WAN or HTTP or Firestore sends you JSON, it is text. When JS parses it, it becomes memory data structure. MongoDB, how JSON becomes BSON, binary JSON. MongoDB never stores JSON. It uses BSON, a binary format. Example, open semicolon bracket code x colon 5 closing semicolon bracket is stored as bytes like /x16 /x00 /x00 /x10 /x05 /x00 etc. Why BSON? It supports dates, supports int32, int64 double, faster to encode and decode, smaller size, fewer disk pages, sequential, which means locality. How is BSON made? Real-world implementation. MongoDB uses C++ to encode or decode BSON. A struct describes field names. A loop writes type byte to length to value into buffer. The buffer is stored on disk. There's no special OS feature. MongoDB implements its own serialization in user space. This is the real-world algorithm. For each key value, colon next line write type byte, next line write key as C string, next line write encoded value in binary form. Next line terminate with null byte. Firestore does the same with its own binary format, not BSON. Is JSON parsed in user space? What language does it? Yes, JSON parsing happens in user space depending on the runtime. Environment, Node.js, JSON parser implementation, V8 JSON parser, language, C++. Environment, Chrome, Edge, VS Code, Monaco editor, JSON parser implementation, V8, language, C++. Environment, Firefox, JSON parser implementation, SpiderMonkey, JSON parser, language, C++. Safari, JavaScript Core, C++, Angular, or Vue. They do not parse JSON. They rely on JS engine. They are transpiled to JS. So all JSON is parsed by the JavaScript engine V8, JSC, SpiderMonkey. Angular, Vue, React are not JSON parsers. They are frameworks written in TypeScript, compiled to JavaScript, running on top of browser's JS engine. They never parse the JSON directly. The browser engine handles it. Now, the part you really want, a code example how React benefits from document DB locality. Imagine this parser document and this React page. So for this parser, you have patient ID, name, consultation, then profile. In React page, const patient page equal patient ID, and then arrow pointing to the right. Next line, const docref equal doc parameter db comma patient comma patient ID, closing parenthesis, semicolon. Next line, const data equals use parser document docref, semicolon. Next line, if not data, return loading, semicolon, then return opening parenthesis div h1 profile card consultation list, and then div closing. Why this is extremely fast? One Firestore read, data come as one continuous binary blob, fewer disk pages. React renders using single JSON, JS object parse, no joins, no multiple round trips, perfect one document, one page mapping. This is why React plus Firestore feel instant. SQL version of the same page, while locality dies, you would need select from patient where ID equal question mark. Next line, select asterisk from consultation where patient underscore ID equal question mark. Next line, select asterisk from allergies where patient underscore ID equals question mark. Minimum 3 tables 2, 3 index lookups, 3 disk 6. React now must wait, const p equals await, db.query select asterisk from patients where ID equal question mark, comma ID. Next line, const equals await db.query select asterisk from consultation where PID, comma ID. Next line, const a equals await db.query select asterisk from allergies where PID equal question mark, comma ID. This introduces more latency, more round trips, more CPU work, more query optimization, more serialization. This is why SQL pages load slower on mobile. How this relates to AWS, Linux, OS, and TCP or IP illustrated. OS, Linux, Firestore, or MongoDB files are cached in page cache. Fewer disk reads. Locality helps OS load fewer memory pages. JSON or BSON, decoding happens in user space. System calls read, write, move data between disk and memory. In AWS, if you host on AWS EC2, DB runs on Linux. Page cache helps. If your database runs on Linux OS, then the page cache of the OS we discussed will help. Firestore Google replicates documents over TCP. Data locality reduces network load. So it helped the network because you only retrieve few I/O, fewer round trips, lower cost. TCP or IP, you learn packets, segments, MTU, NAGL, congestion controls, how it applies here. Concept from TCP or IP, large payload gets split into segments, how it applies to Firestore, MongoDB, React, TCP. Firestore document gets split into packets. Concept from TCP or IP, fewer round trips equal faster. How it applies to Firestore, document DB equal one query, SQL equal many queries. TCP or IP, congestion controls those many small sends. How it applies to Firestore, SQL generate many small queries. Concept from TCP IP, locality reduces packets. How it applies to Firestore, one document equal fewer network packets. Your LiveKit plus Firestore app benefits from the networking theory. Fewer queries equal fewer TCP connection. One document fetch equal fewer packets. Large JSON or BSON fits nicely into MTU aligned segments. Final synthesis, everything connected. JSON, text format, parse in user space. Browser or Node use C++ engines. It becomes JS objects in RAM. BSON or Firestore format, binary, stored with type bytes. Faster plus smaller. Implemented in C++, locality, document DB, sequential pages. SQL equals scatter pages, better CPU cache, fewer OS disk reads. React consumes full documents, fewer renders, less data fetching, maps naturally to nested Firestore doc. AWS plus Linux, page cache helps document DB, Sequential, this reads fewer TCP packets from fewer queries. Next is this. We will just discuss this in the future video. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have 12 more. And we're almost done. 12, 13, 14. And we only have 14 more.